Welcome back to the podcast, everybody. We're going through uniform circular motion, and this is example 11.10 in our notes. And this involves a ride called the rotor. Now, I think gravitron is the generic term for this kind of a ride. I think the rotor exists at Hershey Park, but we've talked about this in class. We have a spinning cylinder, and you get inside of it, and you are forced, or you feel forced against the outside wall. So much that because of friction, you stick to it, and the floor actually drops down to prove that you're actually sticking to the wall, and gravity's not, or that the floor isn't holding you up anymore. You're sticking to the wall simply because of friction. So that's what's happening right here. You, the person wearing your green pants and pink shirt, have a downward force of your mass times your gravity. And if you're going to stick to that wall and not slide down, then you need to be balanced out by an upward force of static friction. So that's going to be one of our suppositions here for this problem, that they have to be in balance with each other. Okay, well, let's start writing down some knowns first. Okay, the coefficient of static friction. That's going to be important. Because think about it for a minute. If there was a very little coefficient of static friction, if somebody came in, if some prankster came in before you went on this ride and sprayed the walls with, I don't know, WD-40 or grease, okay, it would be a lot harder for you to stick to the wall. You'd probably slide right down. So this is going to be important. 0.40, and the radius is 2.1 meters. Okay, well, again, we're going on the assumption that the static friction force between you and the wall, or that is your clothes on the wall, is going to be set equal to your mass times your gravity. Okay, these two forces are going to be in balance with each other. Now let's go a little further here. In fact, I'm going to write this the other way. mg equals static friction force. And the static friction force can be calculated by taking the coefficient of static friction, which we know when we have a given there, times the normal force. Now, in most cases, we've been writing times mg because we're talking about an object on a tabletop, and the normal force is mass times gravity. But in this case, the normal force, and I'll write this in black here, we can see it written here, the normal force appearing to push you against the wall, but really is the wall itself pushing you, accelerating you towards the center, is our centripetal force. Might say the centripetal force equals the normal force. It is, you're basically at right angles. It's at right angles to the wall. That's a right angle line right there. Okay, so that's like saying this is all taking the coefficient of friction times the centripetal force that you're experiencing. Okay, now do we know what that is? Well, we don't, but, well, we're trying to solve for frequency, okay? The frequency that would cause your friction force to balance out your weight force. Can we go from centripetal force right to frequency? No, we can go right from acceleration to frequency, and we can go right from centripetal force to acceleration. So let's state this in yet another way. And again, guys, this is part of solving these types of problems. To know what things are equal to each other and to state them in a number of different ways so that you can find relationships and solve for what you need. So this is just like saying coefficient of static friction, that doesn't change, times the mass of the person times the centripetal acceleration. All right. Let's go one step further. In fact, you know what? Let's just solve for centripetal acceleration. Let's not do this all in one big step. Let's do it in two steps. So we're saying that the weight of the person is balanced out and is equal to the coefficient of static friction times their mass times the centripetal acceleration. So let's solve for centripetal acceleration. mg equals coefficient, mass, the person, times acceleration. What happens to the masses here? Well, they're going to cancel out, and we're going to have our centripetal acceleration is equal to gravity divided by coefficient of static friction. Because these masses cancel out, it doesn't matter what the mass of the person is. No matter what the mass of the person, be they a large person, small person, they will stick to the wall regardless, as long as they all have the same coefficient of static friction between their clothes. Now, I don't know, if somebody went on a water ride beforehand and they're all wet, maybe they have different static friction. I don't know, but for practical purposes, the mass should not matter. So, why is that black all of a sudden? Oh, I know why. Let's solve for our centripetal acceleration and then solve for our frequency, and that's our answer. So that's 9.81 meters per second squared divided by our coefficient, 0.4. I get 24.5 meters per second squared. All right, that's like, I don't know, 2.5 G's, maybe. Not too bad. It's not going to make it pass out, right? So that's our centripetal acceleration. Now we're solving for frequency. If you look in your notes, remember, we have a relationship between centripetal acceleration and frequency. That is 4 pi squared times the radius times our frequency squared. Whoops. So let's simply solve for frequency. Now, remember, frequency is, we want it in, actually, I don't know what we want it in. Let's say RPM. RPMs. That's what we're solving for right there. It really doesn't say. Remember, our standard unit is cycles per second, so we're gonna have to convert that. But let's just solve for frequency first. So for frequency, you see the 4 and the pi and the r. We'll go down the bottom. We divide. And then square root, so that should be centripetal acceleration divided by 4 pi squared times r, which equals 24.5 meters per second squared. That's our centripetal acceleration divided by 4 pi squared, times the radius of 2.1 meters. Four pi squared. I'm doing this a different way right now than I did before, so I don't have this done either. So, and take the square root of that. 0.54. We might say hertz, or 0.54 revolutions per second. Okay, that's our frequency. Let's convert it to RPM, and we'll call that our answer, because RPM is a more standard. Let's see here. Oh, did I do that right? Something looks funny here. Let's try that again. Our frequency is I think I did this right. I mean, the process is right. I think I'm just looking at my math here. Yeah. Hey, sorry about that. Frequency, 0.54 revolutions per second. So 60 seconds in 1 minute. Yeah, sorry about that, you guys. I'm doing this a different way than I originally had. So that would be 32.6 RPM, or revolutions per minute, because our seconds cancel out. Right there. So there we go. That would be our frequency to cause anybody to stick to the wall. Though that would be, you might say, the minimum frequency. If it's spinning around faster than that, then certainly they'll stick to the wall. But that's the very minimum at which the static friction force would balance out with the person of any mass's weight force. And there you have it. Example 1110. If you see any problems or discrepancies, come check with me and let me know. I'll be glad to correct them. And I'll see you in class. Take care.